Okay, so today we're going to continue exploring some of these ideas, and in particular what we're going to consider today is what happens if I take two systems with different states, different microstates, and I join them together and allow them to exchange energy. Okay, so this is going to be the main topic for today. What happens when we have two systems exchanging energy? So in general, the microstates that a certain system can have depend upon its state, and in particular depend upon the energy of the system. So, the accessible microstates depend upon the internal energy What I mean by this is, if the system has some internal energy U1, then there will be a certain network of microstates, which you can cycle between and so on. Okay, so I'll just draw it quickly. You get the picture. This. But if I go to a different energy U2, then I will have a different array of microstates. There will be different microstates at a different energy. And the network and its connections will all be different. When you copy this, it doesn't matter what this looked like, right? It's just symbolic. You can put as many boxes and as many lines as you like. So if I'm at energy U1, then I can go between these microstates. But if I'm at energy U2, then I can go between some different microstates like this. For example, in a gas, if I increase the internal energy of the gas, this increases the average velocity of the particles. Because in a gas, the energy is just kinetic energy. So if I increase the energy of the gas, I must, on average, increase the velocity. And therefore, this changes the microstate. So there are some microstates which correspond to energy U1, and some microstates which correspond to energy U2. And in a closed system, because the energy is fixed, you can't go like this. Okay? So it's not possible to go from a microstate here to a microstate there in a closed system because the energy is fixed. A conservation of energy in a closed system tells you that the energy must be constant, so therefore you cannot go from a microstate here into a microstate there. However, if we take two systems and join them together and allow them to exchange energy, then the system is no longer closed, so it can exchange energy with its environment, and therefore such a transition becomes possible. So if we connect this system to another one with which it can exchange energy, we can then move between microstates corresponding to different internal energy values. So if two systems, I'm going to change this notation because it's going to be a bit confusing for what I use later on. Let me call this one U1 and I'll call this one U1 prime. Because I want to use U2 to label the energy of the second system now. Okay, so if two systems are allowed to exchange energy, then it is possible to go between microstates at different internal energies. So then it is possible to go from microstate at U1 to a microstate at U1 prime. Okay, and it's straightforward to draw a picture for this. Suppose that here's my original thing, it's energy U1, and here I've got energy U1 prime, and let's say that this is equal to U1 minus a certain amount of energy, so minus delta U. So this is again my first system, and within here I've got some microstates I can scatter between them and so on. Okay. And let's suppose originally the other system, I connect the two systems together and allow them to exchange energy. The other system is at an energy U2 here, where it has a certain microstate which are allowed like this. So initially, I can have a microstate here connected to a microstate here. So the combined system is in, first system is in this microstate, second system is in this microstate. Now it's possible to go from a microstate here into a microstate down here if at the same time the second system gains energy. So the second system goes into an energy U2 prime, which is U2 plus delta U. There we go. This. And suppose that I take this microstate here and this microstate here. So now going from here to here is a possible transition, because I would join the two systems together. Okay? And it's a possible transition because the total energy is a constant, right? They are allowed to exchange energy, so the only thing which has to be a constant is the total energy. So U1 plus U2 is a constant. Okay, so just to make sure, let me explain again what's drawn here. I start with my original system, system number 1, in this microstate. I then have another system, system number 2, which is in this microstate. So I have two systems, 1 and 2. System 1 is here, system 2 is there. Now, because the microstates change, the microstate of system 2 will change, and the microstate of system 1 will change. Okay? So these will continually move around here. But it's also possible that this system can lose energy, delta U, and then this system gains energy, delta U, at the same time, because then total energy is conserved. So if the two systems can exchange energy, I can go from these microstates here into these microstates down there. Therefore, the energy of either system can change once they're connected. And in this case, the fundamental postulate tells us something about the probabilities of energy for each system. Okay? So I want to illustrate this with a very simple example. So as there, I'm going to have two systems, system number 1, system number 2, and I connect them together like this, thermally isolated. So they can exchange energy with each other, but not with anything outside. The only energy is only allowed to be transferred between 1 and 2. That's it. So here, U1 plus U2 is a constant, because total energy is conserved. But the energies of each system individually can change. And I'm going to take a very simple example where U1 is either equal to 1 or 2 or 3. So for each of these values of energy, I have a certain number of microstates which are accessible, and check how to do the same as on here. I'm going to take the example where here we have 2 microstates. Here we have 5 microstates. And here we have 3 microstates. So of course in a real system the number of microstates will be incredibly large, billions and billions. But to keep the numbers simple, I'm going to take it like this. Okay? So that's the first system. And the second system, again, I'm going to assume it can either have energy equal to 1, or energy equal to 2, or energy equal to 3. And for each of these values of energy, there are certain accessible microstates, and I'm going to assume that there's only 1 microstate. In that case, 2 microstates here, and 4 microstates here. And finally, I'm going to suppose that the total energy, U1 plus U2, is equal to 4. So the total energy of the combined system is equal to 4. So you see there's various different ways that I can get total energy 4. Right? I can have energy equal to 1 here, and energy equal to 3 here. Right? So I could take a microstate here and a microstate there. That's okay. Or I could have energy 2 plus 2. So I could take a microstate here and a microstate here. Or I could have energy 3 plus 1. So I could take a microstate here and a microstate there. That makes sense, right? So I can either have microstates like this, or like this, or like that, in order to conserve total energy. But you see there are different numbers of possible choices, right? If I have U2 is 1 and U1 is 3, then there's only 3 ways of connecting the microstates, right? I can have this and this, or this and this, or this and this. There's only 3 possible arrangements of the system. However, if I go to the other case, if U1 is equal to 1 and U2 is equal to 3, then I have 8 possible arrangements. Because I can take this microstate with any one of these 4, or I can take this microstate with any one of these 4. Okay? So if the energy is split like this, there are 8 ways of arranging the system. If the energy is split like this, there are 3 ways of arranging the system. Now the fundamental postulate tells you that the probability is equal for each possible microstate. So therefore, this way of arranging the system has a probability 3 divided by the total number of microstates, whereas this has probability 8 divided by the total number of microstates. So what this means is that this arrangement of energy is more than twice as likely as this arrangement of energy. Because if I arrange energy in this way, I have more possible microstates. So that's the idea, and therefore the fundamental postulate tells you something about the distribution of probability of energy when I connect two systems. So let's work it out in detail. So I'm going to introduce some new notation. W1 of U1 is just the number of microstates of system 1 with energy U1. Okay, with energy U1. Okay, so in this example, I've got it here. W1 of 1 is 2, because there are 2 microstates here. Then W1 of 2 is 5, because there are 5 microstates here. And W1 of 3 is 3, because there are 3 microstates here. Right? So this function W just tells me how many microstates are available at each given value of energy. Here there are 2, here there are 5, here there are 3. Okay, And similarly, we do the same for the second system. So similarly, we define the number of ways of having the second system at energy U2. So in this case, you see that W2 of 1 is just 1. There's only one microstate. W2 of 2 is 2, because there are 2 microstates. And W2 of 3 is 4, because there were 4 microstates when the second system is energy 3. Right, so a microstate of the combined system, 1 plus 2, to tell you the microstate of the whole system, I have to tell you the microstate of 1 and the microstate of 2. So I need to specify both. Note right there. So the microstate of the combined system, 1 plus 2, is given by microstate of system 1 and the microstate of system 2. A microstate of 1 and then a microstate of 2. So therefore we can ask, how many microstates of the whole system are there when the first system has energy 1? Okay. The number of microstates of the combined one plus 2, the combined system, is simply the product, right? It's the number of microstates when the first system has energy U1 times the number of microstates when the system has energy U2, with the condition that total energy is conserved, so U1 plus U2 is equal to 4. Now this is exactly what I explained in words before. For example, if U1 is 3, then U2 is 1, then there are 3 microstates of the combined system, because I can have this and this, or this and this, or this and this. So that gives me 3. If U2 is 2, and so U1 is 2 and U2 is 2, then in total I have 10 microstates, because I can choose this one here, then 1, 2, 3, 4, 5, or I can choose this one here, then 1, 2, 3, 4, 5. And then here, I have 8, because I can choose this one and 1, 2, 3, 4, or this one and 1, 2, 3, 4. So the total number of microstates is the number here times the number there. So in this case it's 8, in this case it's 10, and in this case it's 3. So W1 of 1 times W2 of 3 is equal to 8. W1 of 2 times W2 of 2 is equal to 10. W1 of 3 times W2 of 1 is equal to 3. So these are the number of possible microstates of the combined system for different values, for different distributions of the energy. Okay? And if you add these up, you see that in total, the combined system has a total of 21 possible microstates. 8 plus 10 plus 3 is 21. So the combined system has 21 possible microstates. The fundamental postulate tells you that each microstate has equal probability, and therefore the probability of each microstate of the combined system is 1 over 21. fundamental postulate tells you that the probability of each microstate is 1 over 21, because they have equal probability. The probability of each microstate is 1 over 21, because there are 21 microstates, and the probability of each microstate is equal. So now we can calculate the probability distribution for the energy. For example, if the first system has energy equal to 1, then there are 8 microstates for this. The probability of each microstate is 1 over 21, so the probability that the first system has energy 1 is 8 over 21. So therefore, the probability that system 1 has energy has energy U1 equals 1 is P1 of 1. The probability that the first system has energy 1. This is just equal to the number of microstates where that's true, that's 8, multiplied by the probability of each microstate, which is 1 over 21. Okay? And if I write this down as a formula, this is W1 of 1 times W2 of 4 minus 1, which is 4 being total energy, divided by the sum over possible values of energy, I equals 1 to 3, of W1 of I, W2, 4 minus I. This is sum I equals 1 to 3, because there are 3 possible values of energy in this case. So you see this makes sense, right? This is the number of microstates in which the first system has energy 1. This is the number of microstates in total. This is 21, this is 8. So we can do the rest. Similarly, the probability that it has energy 2 is 10 over 21. So the probability that U1 is equal to 2 is P1 2 equals 10 over 21, and the probability that U1 is equal to 3 is P1 3, which is 3 over 21. Okay, so I can draw this on the graph. Probability of U1 and it has 3 possible values, which are 1 or 2 or 3. The probability that it's equal to 1 is 8 over 21. That's about 0.4, so that's somewhere about here. The probability that it's equal to 2 is 10, so that's about a half, that's about here. And the probability that it's equal to 3 is just 3 over 21, that's a seventh, that's about 0.15, so that's about here. So the important conclusion is that the fundamental postulate, when I connect 2 systems together, allow them to exchange energy, the fundamental postulate gives you a probability distribution on the energy of each system. Okay? So therefore it tells you which system is likely to have the most energy if I join them together. So that's the conclusion, so let me write this. Therefore the fundamental postulate okay, I have to write this quite a lot, so from now on I'll just abbreviate this to FP. FP is fundamental postulate. This tells you that if I allow two systems to exchange energy, then it will give me a probability distribution for the energy of each system. Okay, and we've calculated enough to work out the general formula. The general formula is just this. The total energy is U, here 4, and the energy of the first system is U1, here 1. Then I write it something like this. So if total energy is U, then the probability that the first system has energy U1 is given by the formula up there, so let me just write it again. P1 of U1 is equal to the number of microstates where this is possible. This is W1 of U1 times W2 of U minus U1, total energy is U, divided by the total number of microstates. And this is just the sum over a new variable U1 primed, possible values of energy, times W1, U1 prime, W2, U minus U1 prime. Okay. But this U1 prime runs over the possible values of energy. So let me write that. In general, U1 prime goes from 0 to U, where U is the total energy. Okay, so hopefully this makes sense. The fundamental postulate tells you that if I join two systems together, then they will exchange energy such that there's a given probability distribution for the distribution of energy. Okay. Now, it's interesting to consider again what will happen in the thermodynamic limit. Remember, we talked about this limit for the paramagnet before. We've done the case where the systems are small. Okay? And for small systems, we find that if I plot the probability as a function of U, then I get some, distribution like this. So there's a range of possible values of U1, which depends upon the system and the number of microstates. Range of likely values of U1. Okay, but if I repeat it for large systems, it's reasonable to expect, and indeed we'll see that it does happen, that this probability distribution, as the number of particles becomes large, the probability distribution becomes sharp. Okay, and it becomes approximately normally distributed. So you end up with a distribution like this, which is sharp around some critical point, which we can call U1 star. So for large ones, this is only likely values. The only likely value of U1 is that U1 is equal to U1 star for some distribution. So at the moment, I'm just saying this is true, that this, in the thermodynamic limit, it behaves like this. Later on, we'll do some examples to show this does indeed work this way. And again, this is an example of how things get simpler when the systems become large, For small systems, there's a range of possible values, so there's a range of ways they can exchange energy. If I go to large systems, then the ratio of energies, U1 to U2, is virtually fixed. So if I join two large-scale systems together and wait long enough, then there will be a definite ratio of energies between the two systems. Okay, so for two large systems, when connected, the distribution of energy, U1 and U2, take on nearly definite values. The width of their distribution is very narrow. And it's clear how we can relate this to the idea of temperature, right? If I take two systems and I connect them together, then they distribute their energies so that their temperatures are equal, right? For example, if I take a hot cup of coffee in a cold room, then the hot coffee will lose energy and the cold room will gain energy until they reach the same temperature. Okay? So these definite values of U1 and U2 should correspond to those values where the temperatures are equal. Because this is what happens when you connect two systems and allow them to exchange energy. Their temperatures become equal. So these most probable values of U1 and U2 should correspond to the case where the energy temperatures are equal. When I connect two systems together and allow them to exchange energy, they reach an equilibrium when their temperatures are equal. So we expect that this U1 star here corresponds to the state of equal temperatures. Now what we've been able to do by this process then is connect two previously separate ideas. We had this idea we've used here of basically just counting the number of microstates to work out the probabilities. But now we think that this should be related to temperature. Okay? So the distribution of microstates of the system is therefore somehow related to the temperature of the system. Because the most probable value here corresponds to the state which has the most microstates. Each microstate is equally probable. So this state here is the one with the most microstates. It is also the one at which the temperatures are equal. So there's a correspondence between two systems having equal temperature and the number of combined microstates being maximum. So we can find it. We can find it. What is the most probable value of U1? So in general, what is the most probable value of U1? And this should correspond to the state where the temperatures are equal. Right? What is the most probable value of U1? Well, from the formula down there, the probability of U1 is proportional to the number of microstates of U1 times the number of microstates U2, where U2 is just U minus U1. So the probability is proportional to this. Okay? And at the maximum, the derivative of this distribution with respect to U1 should be equal to 0. So at maximum, the derivative of P1 with respect to U1 should be equal to 0. Okay? And if we see what this condition implies, then we get a condition that the temperatures of the systems are equal. Okay? So I've defined P1 as a function of U1, so let's just differentiate it and see what we get. So first of all, I differentiate W1 with respect to U1, so this gives me W1 by du1 times W2 of U2. Then I can differentiate W2 by du1, so remember that U2 is a function of U1, so this just gives me minus W1 of U1 times, sorry, these are exact derivatives. This thing should be equal to 0. Okay, so this is the condition we get. Now we can rearrange this quite simply to get a nice symmetrical form. This means that 1 over W1 of U1 times dW1 by du1 should be equal to 1 over W2 of U2 times dW2 by du2. Okay, that's simply rearranging the equation. And then finally, I can write this in the following form. This means that d by du1 of the log of W1 should be equal to d by du2 of the log of W2. Okay, this last step, let me just explain it a little bit more because it might be unclear. What happens when I differentiate the log of the function, right? If I have d by dx of the log of f of x, then first of all I differentiate the log, so that gives me 1 over f of x. And then I differentiate the thing inside here, so that's df by dx. And you see this is exactly what we've got here. It's 1 over the function times the derivative of the function. 1 over the function times the derivative of the function. So that explains this step. But now, I'm very nearly finished. This must be a condition on the equal temperatures, because this is the condition where P1 of U1 is a maximum, and I said that when P1 U1 is a maximum, then the system has equal temperatures. So this condition must be a condition for equal temperature. So that's the main point to conclude on. So this condition must be equivalent to the statement that T1 is equal to T2. Because at the maximum probability, the temperatures should be equal. So therefore, we identify this function with some function of the temperature. Okay? And we'll see next time that, in fact, d by du of the log of W is equal to 1 over the Boltzmann constant times the temperature of the system. Okay? So this is the connection between the two, but we'll see this next time.